no problem.
Okay, great. Thank you.
Okay. So I wanted to talk about an interaction between group theory and metric spaces, between algebra and analysis, and this was discovered really by Mostow, by Gromov, and by Mostow. And so I want to also take the opportunity to present some joint work with some of my collaborators, Ville Kivioja from Finland, Enrico Donne from Switzerland, Sebastiano Nicolussi Golo from Italy, and for Allessandro Ottazzi, who lives in Australia. So we want to look at Lie groups, but use methods from metric spaces. So let me just remind you what is a metric space. I'm sure that everybody knows this, but just let me remind you. So we just take a space with a distance function that satisfies absolutely standard axioms, positivity, symmetry, and the triangle inequality. And I just wanted to say that an isometry, when I talk about an isometry of a metric space, I always mean a function that is invertible, because that's somehow a necessary hypothesis in some of the things that I say. And when we have a dilation of a metric space, we mean that this is an invertible function, so that the distance between delta x and delta y is some multiple, some fixed multiple of the distance between x and y. So it just makes everything get bigger or everything get smaller. So these are just standard definitions that I'm. So for example, we can take the vector space Rn with various distances. There's a distance that's associated to the little LP norm, and it's particularly nice to take the case of the one distance or the two distance. And there's a bit of a difference between these two cases, where you can take the same space with different metrics and you get rather different results. So in both cases, translations are isometries. And when P is equal to 2, then all the rotations are isometries. But if P is equal to 1, only rotations through whole multiples of pi over 2 are isometry. And so I wanted to show you. So here's a map of an American city in which all the roads go either north-south or east-west. And if you rotate the map through 90 degrees, it could easily be another map of another American city. But if you rotated it through 45 degrees, then there would be no American city that would look like that. So another example, of course, is the unit sphere, with a difference that's defined by the inverse cosine of the inner product. And that corresponds to taking a sphere. When you take 2 points on the sphere, then the distance between them is actually equal to this angle. And that corresponds to the distance along the great circle on the sphere that joins the points P and Q. So these are very easy metric spaces. Now, here are some less trivial examples.
What is the last line you said? In both cases, rotations are, and there are no dilations. Okay.
There are no dilations. You can't dilate the sphere at all, yes, because the sphere has got some kind of fixed radius, and if you dilate things, then you would have to change the radius of the sphere. So people who work on subelliptic differential operators often use the Heisenberg group as an example, and there are groups that are like the Heisenberg group, but the Heisenberg group can be written as the set of pairs ZT, where Z is complex and T is real. There's a multiplication law that is like addition, but with some extra factor that makes things a little bit different. And very often this group is given the Corani distance, and the Corani distance is more or less defined by saying that the distance between points H and H prime is the same as the distance between points G, H.
I think
Mr.
you are
Cowling,
mute.
Can you
Yeah.
Yeah.
Okay, can you hear me now?
Yeah.
Yeah, absolutely.
Okay, good. Okay, so the Corani distance is a distance that has an invariance property, and if you look at the distance of points zt from 0, 0, then it's given by an expression mod z to the fourth plus mod t squared to the power 1/4. So this is very standard for people who study the Heisenberg group, who study certain subelliptic differential operators. And my next example is, oh dear, now I've lost my page. So let me go back to the beginning. And in complex analysis, people who do research in complex analysis in several variables, often they work with the boundary of the unit ball in Cn with a distance between points z and w. So the z and w are both n vectors lying on the units here, and then you take the absolute value of 1 minus w bar times z, and then you add these up. So this is essentially the complex inner product of the vectors, and then you take 1/2 power of that. And these two metrics are a little bit exotic in the sense that neither of these is a Riemannian metric. This distance treats the t direction very differently from the z directions, and this distance, if you fix w, then it treats the w direction very different from directions that are orthogonal to w. So these are slightly more complicated metrics, and these are more or less examples of something that are known as sub-Riemannian metrics. So here's another example. I can take GLNR to be the group of invertible n by n matrices, real coefficients, and I can make that into a metric space just by taking some kind of Hilbert norm. This Hilbert norm is not a translation invariant metric on the group GLNR, but it's possible to modify it in a way that makes it become translation invariant. And more generally, if I've got a group with a left translation invariant metric, then I'll call that a metric group. If it's also a Lie group, if it's also a closed subgroup of GLNR, then it's a metric Lie group. And the Heisenberg group and the vector space are examples of metric Lie groups. So I have some examples of metric spaces, and here is a sort of a very general theorem that goes back to 1928 by two German mathematicians, Van Danzig and Van der Waerden. And if I take the collection of isometries of a metric space, then first of all, there are several natural topologies to consider on this space of isometries. So there's what's known as the compact open topology. There's the topology of pointwise convergence, or there's the topology of uniform convergence on compact sets. And it turns out that these three standard topologies all coincide on this when I'm just looking at isometries of this space. And since these three topologies coincide, this is kind of nice, and it allows you to say interesting things about.
Here you are taking M to be a Riemannian manifold, or what? What is the condition on M?
Sorry, I can't hear you.
So what is M here? It is a Riemannian manifold or any kind of?
It's just a metric space.
Just metric space. Okay.
Just a metric space.
Okay.
So if I take just a metric space, then all of these topologies coincide. I can get a topological group, and the topological group has also got a natural metric on it. So this is a very classical theorem, and it says that the isometry group in some sense is a nice group. So I don't want to talk about Riemannian metrics. Well, I'll have to talk about Riemannian metrics, but I want to talk about general metrics, and at the end, I hope to explain why it is that I want to talk about general metrics and not just special metrics. So we've got M, a metric space M with a space M with a metric D is a homogeneous metric space. If the isometry group acts transitively on it, that is, for any 2 points, I can find an isometry that maps one point to the other one. So the examples that I gave and the isometry group are homogeneous metric spaces, but in real life, there aren't so many homogeneous metric spaces. Everything in the world is somehow irregular and bumpy, and homogeneous metric spaces are idealized models of things that we might have to deal with in the real world. Okay, so let me come up with a different example. If
the unit sphere of an infinite dimensional Hilbert space is also homogeneous?
Sorry?
Unit sphere of a Hilbert space is a homogeneous metric space.
Yes, I guess actually that I'm restricting to locally compact. I haven't said this, but I probably should. I'm particularly interested in locally compact metric spaces. So actually early on, I should have said, even for this theorem here, I want to talk about locally compact metric spaces.
Okay, thank you.
So here is a different kind of example. If I take a finitely generated group, so G is a group and S is a finite subset. So for instance, G could be the set of n vectors with integer entries under addition, and S, which would generate it, could just be the standard basis vectors. And if I take these standard basis vectors, then obviously I can generate any element of Zn using these. And in fact, if I'm dealing with integer entries, then everything can be written as a product of generators to a power either +1 or -1. And I can define the length of an element of the group as basically the number of generators that I need to be able to write it down as a product. And so this is a discrete example rather than a continuous example of a metric space. And if I take in this group if you like, the ball of radius k, the set of all elements whose length is at most k, then we say that the group is of polynomial growth if there is some constant and an integer so that the cardinality of the elements of length at most k is less than or equal to this constant times k to the integer. And it turns out in group theory, and this is maybe somehow one of the fundamental theorems of what is known as geometric group theory, that if the group is of polynomial growth, then you can get a different generating set, and you might change the constant, but you don't change the fact that it's of polynomial growth. So that's another example of a group that is a metric space, and it's not a continuous group at all. So let me now tell you a famous theorem that is due to Gromov. First, I should tell you what I mean by a nilpotent group. So if I get a group of G with an identity E, then I can form a commutator subgroup. Well, if H is a subgroup, I can form the commutator subgroup of G and H, the smaller subgroup that changes all of the commutators X, Y, X to the minus 1, Y to the minus 1, where X is in G and H is in H. And then we can define what is known as the lower central series of G. We start out with the group, and then we take commutator of G with itself. And then for the next one, we take the commutator of G with G2. And for the next one, we take the commutator of G with G3. So inductively, J plus 1 is equal to the commutator subgroup of G to Gj. And the group is said to be nilpotent of class J or of step J if J plus 1 is just the identity. So if you keep on taking commutators, then in the end, you get to the trivial subgroup. And Gromov's theorem is the following, that if we have a finitely generated group of polynomial growth, then there is a subgroup G0 of G, so that the quotient space G over G0 is finite. In group theory language, G0 is a subgroup of finite index, and G0 is nilpotent. So this is saying that every finitely generated group of polynomial growth is almost nilpotent, is a finite extension of a nilpotent group. This theorem was proved by Gromov in 1981. So, okay, so this is a theorem in algebra. It just says that the group is nilpotent. But interestingly enough, the proof uses ideas from analysis. And let me say a little bit about Gromov's proof. So if I define the distance between G of H to be the S length of G to the minus 1H, then it turns out that this is an example of a metric group. In other words, it's a metric and it's invariant under translations in a natural way. And what Gromov did, and I have heard said, but I'm not sure whether this is true or not, but I've heard said that Gromov was a Russian mathematician, but he went to live in France. And this was a time when it was very bad for Russian mathematicians to live in France. But he proved a number of theorems, including this one. And if he had been living in Russia, he probably would have got the Fields Medal. But since he was living in France, he couldn't possibly get a Fields Medal. So anyway, how does Gromov's theorems work? So he invented a way to rescale the metric space. GD, this is this metric group, and he obtains a new metric group, which is collected and has a dilation. So let me try to describe this process a little bit. So imagine that we have a very simple case. Imagine that we have the integers. So if we take the integers and then we rescale it, we get not just the integers, but we get all the numbers that are integer multiples of 1/2. And if we rescale it again, we get all the numbers that are integer multiples of 1/4. And if we rescale it again, we get all the numbers that are integer multiples of 1/8 or 1/16 or whatever. And if we continue this process and take some kind of union and some kind of completion, then out of the integers, we can construct the real line. And what Gromov invented was a way to rescale a metric space to obtain a new metric space that in the case of a metric group gave a new metric group, which was connected and in fact has a dilation. So it's a nice group with a dilation. And we've said what we mean by dilation. That's a purely metric concept. So sometimes you may see people talking about Gromov-Hausdorff distance. And so Gromov sort of thought quite hard about metric spaces and came up with some new ideas about metric spaces and how to look at these. Anyway, he showed that this limit group that you get, that this limit group, which is a connected group, is nilpotent. It actually turns out to be a nilpotent Lie group with dilations. So it looks something like the Heisenberg group, possibly more complicated. But this information can be used then to say that G is almost nilpotent. But here we have an example of a theorem in group theory, because it's a theorem about metric groups, it's a theorem about finitely generated groups, and it's just proved using ideas of metric spaces. So let me just give you one definition for metrics, another definition for metric spaces. If we want to compare metric spaces, then very often what is used is a concept of quasi-isometry, and we say that two metric spaces are quasi-isometric if there is a mapping so that in the image space, the distance in the image space is comparable to the distance in the original space up to some constant and possibly also up to an additive constant. And it turns out that this idea of quasi-isometry in metric spaces is quite a useful thing. And in particular, if we're looking at a finitely generated group, then we can find different generating sets. And if we take these different generating sets, then it turns out that the group that we get with the metric associated to one generating set and associated to the other generating set are quasi-isometric. So there is a natural notion of quasi-isometry, and this can be used to show that this theory of Gromov doesn't depend on what generating set you take. And let me just remark that it's useful to deal with what is known as 1C quasi-isometry. So in this inequality here, you just take L is equal to 1, and it says the distance between image points is close to the distance between the original points up to some constant. And if the points are a very long way apart, then that means that these distances are really very comparable.
Professor Cowling, you don't assume phi to be surjective?
I guess yes. I'm not assuming actually surjectivity, but I'm assuming some sort of almost surjectivity, so that if I this second condition is saying that every point is within a fixed distance of an image point. So for instance, an example would be that the integers are quasi-isometric to the real line.
Okay.
So, I mean, the mapping from the integers into the real line is certainly not subjective, but every point there's some fixed distance between any point and an image point.
Right.
So this would be an example of a 1-1 quasi-isometry, or maybe 1/1/2 quasi-isometry.
Thank you.
Okay. So let me tell you another famous theorem, and this is really a theorem in topology. So a symmetric space is a Riemannian manifold. I'm going to assume that it's, I mean, I should actually say of the non-compact type all the time, but to say this lots and lots of times would be very boring, so I won't say it. But it's a contractible Riemannian manifold. It's one that looks like Rn, essentially, with a symmetry about every point, and a symmetry is an isometry that fixes the point and whose differential at the point is minus the identity. So near the point, it's some kind of reflection in the point. And it turns out that every symmetric space can be written as G over K, where G is a semi-simple Lie group and K is a maximal compact subgroup. And then there is a locally symmetric space, which I'm going to take to be a compact Riemannian manifold that is locally isometric to a symmetric space. So here I'd be thinking of something that might be like a union of two toruses or something like this. And every locally symmetric space has got a universal covering space that is a symmetric space. And that means that every locally symmetric space is some kind of double coset space where G over K is a symmetric space, and then I divide out by a subgroup of G. Anyway, Mostow's theorem, Mostow's rigidity theorem, that once again was considered to be something that might have been worth a Fields Medal, but Mostow proved it when he was over the age of 40, so it was clearly not good mathematics. He showed that if you have two locally symmetric spaces that are topologically homeomorphic, so they're topologically the same, then they have to be geometrically isometric, possibly after a change of scale. And there's an exception in dimension 2. So this is saying that two spaces that look the same topologically, so a donut and a coffee cup, for instance, are examples of two spaces that are topologically the same. Then they have to be geometrically the same. And this was considered to be quite a remarkable theorem, that from a very weak form of similarity, you got a much stronger form of similarity. So maybe for reasons of time, I will skip over the proof, but it's quite a long and complicated proof. There's a book in the Annals of Mathematics series that's about 100 pages long, in which all of the details are given. So it's not by any means a trivial proof, and it can't really be summarized properly in the space of one paragraph, and so this paragraph is not really very, very good. But in any case, Mostow's proofs later were improved and extended and generalized and so on. So anyway, out of these classical and important theorems, there sort of rise a number of questions that you can ask, just trying to sort of clarify what all of this means. So one is, what can we say about the structure of a connected metric space with a dilation? So in Gromov's theorem, one constructed the so-called asymptotic cone, which was a connected metric space with a dilation. And then this question is about what can we say about these things? And Gromov says that if the connected metric space is if the metric space is a connected group, then it's a nilpotent group. But what if it's not a group? What can we say about metric spaces that just have dilations? And the second question, and this one comes out of also Mostow's theorem as well as out of Gromov's theorem, if we get two connected metric groups that are isometric or are quasi-isometric, does that mean that the groups are isomorphic? And more generally, if I take two connected homogeneous metric spaces that are isometric or quasi-isometric, do they have to come from isomorphic groups? And in some sense, in both Gromov's theorem and also in Mostow's theorem, there are examples where you take metric spaces that turn out to be quasi-isometric, and then they have to come from isomorphic groups. So is there a general theorem here? Are these both particular cases of some general theorem? So these are the questions that I thought about with my colleagues Kivioja, Donne, Nicolussi, Golo, and Ottazzi, and we have an answer to this question, but let me begin by reminding you about factorizing matrices. And it's very well known. It's somehow very standard in applied mathematics in particular that any matrix, any general invertible matrix can be factorized as a product of an upper triangular matrix and an orthogonal matrix. And in fact, if one goes to Wikipedia, which is the source of many good things in mathematics, one can find out about these decompositions. And there's quite a long article about these decompositions, and it's related to the Gram-Schmidt process, but the Gram-Schmidt process is not very good numerically, so that people who are trying to do this numerically have other ways of doing it. But in any case, we don't need to know the details of this. We just need to know that any matrix can be factorized as a product of an upper triangular matrix and an orthogonal matrix. And this means that if I take the space of upper triangular matrices and the space of often orthogonal matrices, then I can write GLNR, I can sort of factorize it as a product of one of these groups with the other of one of these groups. Now, this is a funny product of groups because it's not a direct product, it's not a semi-direct product, it's just topologically it's a direct product, but in group theoretic terms, there's not very much good about this decomposition. So that's just well-known facts about matrices. So in my work with these other people, we proved a lemma. So the lemma is about groups and compact subgroups. So anytime I have a metric Lie group, so a Lie group with a metric that's got some natural invariance properties and a compact subgroup, then there is a new metric on G and some constant, so that the new metric has got extra invariance properties. The new metric is invariant under the action of G on one side, but it's also invariant under the action of the compact subgroup K on the other side. And so this is a sort of an extra nice metric, and the group G with the original metric and the group G with this new metric are 1C quasi-isometric. That means that locally you can't say very much, but at large scale they look very, very similar. So this is a lemma, I should say something about the proof. And for the proof, a key step is just to define this metric. If you don't, you know, when you've got to prove that something exists, then one way to do it is just to define it. And once you've defined it, then there's a way, then you can reasonably hope to be able to prove the things that you want to prove about it. So here's the definition. So it's defined with an inf and a sup. And this is a rather strange definition. And in particular, I should point out straight away that even if I start out with a very nice kind of a metric, a Riemannian metric, then as soon as I start taking sups and infs, then what I get is not a Riemannian metric. And so this is a kind of strange metric that it's a bit odd. Clearly, it's not Riemannian, even if the original metric is a nice Riemannian. But nevertheless, once you have this definition, you can check these things. The invariance property follows more or less immediately from the definition, and then the quasi-isometry. Well, you're sort of seeing what happens when you change things over compact sets, and when you change things over compact sets, there's always a bound on the metric, and so you can prove that these spaces are almost isometric. So this lemma is a key step in proving a theorem. And the theorem is that if we've got a metric Lie group that's got a factorization where S and K are closed subgroups, but I'll think of K as being compact, and if you like, we could think of S as being solvable, then if dk satisfies the condition which was on the previous page, this double invariance condition, then there exists a metric on the direct product of these groups. So that G with the metric dk and S times K with the metric D times are isometric. So this means, for instance, that if we take something like SLN, which we know can be written as a product of upper triangular matrices and orthogonal matrices, if we put the right kind of metric on this, then it's actually isometric to a direct product of a solvable group and a compact group. And this is, well, once again, the key step is to define what the metric is, and the definition is actually not so hard, but then once you know what the definition is, then it's easy to check that it actually is an isometry. So it turns out that there are some examples of this kind. One is due to John Milner, another one is due to some people who work in sub-Riemannian geometry, Agrachev and Barilari, but their arguments are complicated and they're limited to only certain kinds of metrics. And we can give a completely general proof of this that really is better. Now, this means that I mean, for instance, the group GLNR is not in any way a direct product of a solvable group and a compact group. but it is nevertheless isometric to such a group. And this means that we can construct examples of groups that are isometric, but are absolutely not isomorphic. And this suggests that Gromov's technique of using metric ideas to prove group theoretic results may not always be applicable. And so that's that says that there's no big general underlying result that generalizes simultaneously Gromov's result and Mostow's result and so on. Now, here is a comment that it would be really nice to be able to do with what are known as sub-Riemannian metrics. Sub-Riemannian metrics are like Riemannian metrics, but with a Riemannian metric, you have a good way of measuring the length of a curve. With a sub-Riemannian metric, you're only allowed to take curves that move in certain directions. And then you can take the lengths of these. And the sub-Riemannian metrics are actually, it turns out that both Gromov and Mostow end up using sub-Riemannian metrics in their arguments. So the other question I raised was what about dilations? And so about dilations, let me conclude with another theorem. If I take a locally compact connected homogeneous metric space with a dilation, then there is a nilpotent metric group and a dilation of the metric group that is both a group automorphism and the metric dilation, and an isometry from the metric space to the metric group, so that behaves nicely with respect to the dilations. So this theorem says that in fact every metric space with a dilation, every locally compact and connected homogeneous metric space with a dilation is actually a nilpotent group. So this is in some sense a good theorem because it says that any metric space of this kind looks like the groups that Gromov was dealing with, but in any case, the proof of this is more complicated, and I guess I should probably I can either stop now or I can give you a summary of the proof in a couple of minutes. Which do you prefer?
I think you can give summary of the proof in a couple of minutes. Yeah. Okay.
So let me do this. So I'm going to write G for the connected component of the identity in the isometry group and delta for the dilation. So the first thing is that the Banach fixed point theorem says that if you have a dilation of a metric space, it has a fixed point. And then the next thing is that the metric space has to be a proper metric space. That means that compact sets have got finite diameter, and sets of finite diameter are almost compact. And it's also doubling, which means that if I take a ball of double the radius, then I can cover that by some fixed number of copies of balls of the original radius. And if I want to prove these conditions here, I prove that they're correct when R is small, and then the dilation allows me to prove it when R is big. Somehow, proving things when R is small is quite easy because the space is locally quite well behaved, but it might be bad at large scale, but when there's a dilation, it can't be bad at large scale. So the next step is to show that we have a contractible analytic manifold, and this follows essentially from the solution to Hilbert's fifth problem. Hilbert's fifth problem was whether was what we could say about groups that were locally isomorphic, and it turned out that in a group that is locally isomorphic to a Euclidean space, then the multiplication is actually an analytic function of the coordinates. And essentially we use this, and then so after we use this, we show that the isometry group is a Lie group. The space on which it's acting has to be a quotient of the Lie group. It has to be a manifold, and it has to be locally contractible. And locally contractible with a dilation means that it's contractible. Then it's doubling, and proper is polynomial growth. So then we get something of polynomial growth. And finally, we know something about Lie groups of polynomial growth, and we apply that, and in the end, it turns out to be nilpotent. So I want to end up actually with a question, and the question is that it seems to be clear that there are various important theorems in Lie theory that use metrics that are more general than Riemannian metrics. And the question is it enough to deal with sub-Riemannian metrics? And that means, is it possible to prove the theorems that have been proved using sub-Riemannian metrics, or using what sometimes are called Carnot groups, or things like that? So that, I think, is everything that I wish to say, and I'm happy to try to answer questions.
Okay, so thank you very much, Professor Cowling. So is there any question that people would like to ask? Yeah, so there is one question in the chat box. It's called, is the change of scale global or local in some sense?
Okay. So I'm not sure which page the change of scale was on. So I think the change of scale was probably in Mostow's theorem. So let me go back to that. So if we have some locally symmetric spaces, so these are Riemannian manifolds, and then that are topologically the same, then they are geometrically the same, possibly after a change of scale. There is one constant that is a global change of scale. So I guess that, I hope that answers the question in the chat box.
Yeah, so Professor Ajit Iqbal Singh, does that answer your question?
I have a small query, Professor Cowling.
Okay.
Hello.
Yes, yes.
Hello?
Yeah, please go ahead.
Is it true that doubling metric spaces can be, quasi-asymmetrically embedded in a Hilbert space?
Let's say that I know of a number of theorems of this nature, but I don't know what is the status of the general theorem, I feel like. So certainly there is interest in, what kind of metric spaces can be embedded in Hilbert spaces, and there are certainly quite a few theorems about these, but this is not something that I'm an expert on, and I'm afraid that I don't remember the answer to that question, and I don't even know if it is known in general.
Mm-hmm. Thank you.
So is there any more questions?
Actually, why I asked this thing is because the Heisenberg doesn't Lipschitz-ly embed into Hilbert space. So I thought maybe for doubling metric spaces, this weaker statement may be true.
Well, I think that there are certainly theorems about embedding. Well, let's say that the Heisenberg group and its high dimensional analogs have been studied very intensely, and there are lots and lots of people who know lots and lots of things about this. But I don't know what happens once you get away from Heisenberg groups.
Okay.
So I'm sorry, I really am ignorant about that question.
All right. Thanks.
Yeah, so I have a small question here. Yeah, sure. Yeah, go ahead. Somebody was asking something, right?
Maybe they need to unmute.
Yeah, so somebody, okay. Okay, so I have a small question here. Okay, so the question is that you talked about sub-Riemannian metric. Whether
Yes.
this question will be, yeah. So is it the same as this so-called semi-Riemannian metric? I mean, the one with signature P, Q, which appear.
Okay. So a Riemannian metric always gives a positive distance between points, but the metrics with signature PQ can give sort of negative distances or imaginary distances or things like that. So no, the sub-Riemannian metric is something where you define the distance between 2 points to be the minimal length or the infimum of the lengths of curves that join them, and you look at curves that are what they usually call admissible curves. Admissible curves are allowed to go in admissible directions. This is something that is somehow very natural in engineering, and people in control theory and engineering use this a lot. But so here is an example. If you have a car, an automobile, then of course this drives naturally forwards and backwards, but it doesn't drive sideways very well. But you can still make it go sideways by making it go forward and then making it go backward and making it go forward and backward, and you can see people parking in a parking space by a process of going backwards and forwards. So sort of the going sideways is not an admissible direction, but nevertheless, even though it's not an admissible direction, by going backwards and forwards, you can still end up going in that direction. And in the case of the Heisenberg group, at each point, so in the case of the Heisenberg group as a Lie group, there are naturally 3 vector fields that span the Lie algebra. And one of them at the identity is, if you like, sort of ddx, another one is ddy, and the third one is ddt. And ddt is the central one. And then when you take left invariant vector fields, the ddx becomes something like ddx plus y ddt, and the ddy becomes something like ddy minus x ddt. And so at each point, there the x and y give you a span a two-dimensional subspace of the tangent space. And in the Heisenberg group, if you want an admissible curve, you are only allowed to go in those two directions at any point. So you have to take a curve that is the so-called admissible curve. And in the case of the Heisenberg group, if you want to go in the t direction, it turns out that the best way to go in the t direction is actually to go in some kind of corkscrew-shaped curve that goes around in circles and rises gently. Because as soon as you change x and y away from 0, then you're allowed to have some DDT in what you do, so that you can actually end up going in those directions. But you can't, from the origin, you can't go directly in that t direction. So a sub-Riemannian manifold is one way you've got restrictions on the directions that you go in, but it turns out that the sub-Riemannian manifolds are sort of appear naturally in Mostow's proof. They appear naturally in Gromov's proof, and they seem to be quite popular in various parts of mathematics. And maybe it would be possible to do everything with just sub-Riemannian geometry. I don't know what the answer to that is, but it would be nice if that was the case.
Okay. So thanks for the elaborate explanation. I mean, I got a feeling of it. So thank you very much. So is there any more questions?
Yeah, I have a question. So about the symmetric spaces, I mean, Riemannian symmetries, we have a description of that in the form G over K, right? For semi-simple group or whatever. So
Yes.
Is there some such thing for sub-Riemannian manifolds? I mean, some class of sub-Riemannian manifolds. Is there any such a description similar or
no, I don't think that is the case. I don't think that is the case. But
at least
even in the case of semi-simple Lie groups, there are some sort of natural sub-Riemannian or sub-Laplacians and things that occur. For instance, if you have a G over K, then there's also some kind of complementary P, and if you take the sum of all of the squares of the derivatives in the P directions, then it turns out that this is an example of a sub-elliptic operator, and in fact there are papers by various people such as Dietrich Miller about the harmonic analysis of this sub-elliptic operator. So there are some sub-Riemannian things that do occur in this case, but I think in general, we don't know very much about sub-Riemannian geometry. After all, Riemannian geometry has been around for a long time, and there have been some very smart people who have thought about it over the course of time. I mean, apart from the original people, the Einsteins and so on along the way who thought about it, I mean that it's had a chance to develop rather more than sub-Riemannian geometry.
Yeah.
Okay, so Professor Cowling, I'm